All right, let's talk about extrema on an interval. Basically, when I'm talking about extrema, I'm talking about maxes and mins. So we got some definitions to read through here. This is something that at first was a little bit hard for me to understand, but once I thought of it in these terms, it made a lot of sense. If you have an open interval, which means that A is not included in your interval and B is not included in your interval, then it's going to be a relative max and min. Okay? Then you're looking at a relative max and min. If you have a closed interval, meaning A is included in your interval and B is included in your interval, whatever A and B are, then it's an absolute max and min. So this general rule is really, really helpful for determining whether we're talking about a relative or an absolute. Let me give you an example of relative. This is mainly review, but let's say you had a function that looked like this. Well, this would be a relative max and a relative min because there are other points on this function that are higher than this max, and there's points on this function that are lower. But let's talk about what an absolute is. If I had like a parabola, right, the vertex here is an absolute max because there are no other points ever that are higher than this point. So that's just what an absolute is and a relative is. But remember, when you see open intervals, you're going to be talking about relative. When you see closed intervals, you're going to be talking about absolute maxes. These are some other terms you might see: local max and min, global max and min. These just mean the same thing as either absolute. Global means the same thing as absolute, and local means the same thing as relative. All right, let's go to the next page. Okay, so we got some examples of just what an absolute max looks like, what a min looks like. So this one just says find the maximum and the minimum. And it looks like we have a closed interval from -2 to 1, so we're going to be talking about an absolute max and min. And it looks like we have an absolute max, I'll just fill it in here, at x equals -2. And we can see that because when x is -2, this function is at its highest point. Now we could figure out what that is by plugging it into this equation. So what is that absolute max? Well, it's f of -2, and f of -2 is -2 squared plus 1. -2 squared is 4, plus 1 is 5. Okay. What about the absolute min? Well, we can tell that that happens right here at 0. So we could say there's an absolute min at x equals 0. And again, we could just plug that into our function, determine what that minimum is, and that would be 0 squared plus 1, so it's just 1. Okay, so this is some language you got to be familiar with. The at tells us the x location, and then the max or min itself is the height, and that would make sense because that is the maximum height or the minimum height. Okay, let's go to example 2. All right, so notice that you have a open interval here, so that means we're going to be talking about relative maxes and mins. And the key thing to notice here is because it's open, we don't actually know when the maximum is. So there is no max here because there's no point that we can definitively point at and say, yeah, look, that is the highest point. Because it's open, -2 is not included, and the number that is closest to -2 but a little bit greater than it is, we can't define that. Because is it -1.9? Is it -1.99? Is it -1.9999999? And so on. You can't really define that. So that's why we can't actually definitively say there is a max. However, we can still say that there is a relative min. And same thing. It's the same function. So it's still at x equals 0. And just like the last problem, it's f of 0, which is 1. So we do have a relative min here. Only difference here, right, is that this is an open interval, and that's why these two things are open, because we don't actually include those points as opposed to a closed interval where we'd get an absolute max. Okay, let's do another one. Find the maximum and minimum, and now we have a piecewise function. Notice that it is defined at x equals 0, but there's a jump here. It just jumps up to the value of 2. The rest of the time it's taking on this same function. It is a closed interval. So we do have an absolute max, same as before on example 1. It's an absolute max at x equals -2, and that's when, sorry, it wouldn't be f anymore. It would be g of -2. And if you plug in g of -2, you still get 5, just like we did on example 1. So we do have an absolute max. But there is no absolute minimum here because we don't know what the point is that is the lowest. Again, it could be 0.1, 0.01, 0.0001, and so on. So there is no absolute minimum. And then it jumps up here. This isn't a minimum either because there are no points to the right or left of this that are a little bit higher. So this is not a minimum either. So there is no minimum here. There's no way to determine what a minimum value would be, so it does not exist. So maybe you might want to say minimum does not exist. Maybe just a little note. And then the same thing on the problem up here. You could say maybe that the max does not exist. Just a note. It's not really part of the answer, but just a way of thinking about it. Okay, let's go on to one more page. Okay, so this is asking a slightly different question. It's just asking, does the derivative exist? And we're asking this because that's going to help us kind of determine when there's a max or min, because it's not only, in the other ones we noticed that there was a max or min at curve. So let's talk about that real quick, right? So if you notice we had something like this and there was a max there. Well, wouldn't the derivative equal 0 right there? And or it would be an endpoint, right? We had endpoints too, and that's how we got maxes. So it was either that the derivative was 0, or on the endpoints is actually when the derivative doesn't exist because we don't have any information to the left or to the right. So there's another situation where we could get an absolute max or min, and that's when the derivative doesn't exist. And we'll notice right here, the derivative does not exist because, if you think about it, there is no tangent line to this point. It's a sharp corner, and so there is no tangent line because you could have a tangent line like that, you could have a tangent line like that, you could have a tangent line like that. There's actually infinite tangent lines that can go there. And so the derivative does not exist. And so we're going to say that f of x does not exist. And so this is another candidate for an absolute max or min. And in this graph we could tell that it is at least a relative min. We don't know if we're talking about an open or closed interval. Seeing how there is no interval here, I would just say that we'll just assume that it's open for now and just say that it's at least a relative. But if this went on and on forever, if the interval was negative infinity to positive infinity, then we could say for certain that this is the absolute min because these things just go on and on and on up in either direction. So, but that's all they wanted us to know there. Does the derivative exist? How about on this problem when you have a cusp? Another situation where the derivative does not exist. So f prime of x does not exist. And I guess I should say f prime of 3 does not exist. See, the derivative does exist, but it's not defined at 3. So we can actually do this. The last one we didn't really have a way to take the derivative here, but on this one we can. We could take the derivative here. So let's just do it so we could see why is it not defined at 3. Well, if I take the derivative, I would get 2/3 times x minus 3, and 2/3 minus 1 is negative 1/3, and then the plus 1 turns into a 0. I would have to account for chain rule except for the derivative of the inside is just 1, so I don't really have to worry about it. So as I simplify this, I would end up with 2 over 3 cube root of x minus 3. And now you could probably see why it doesn't exist when there's a 3. If you plug a 3 in here, you get 3 minus 3 is 0, the cube root of 0 is 0, 0 times 3 is 0, and you get a 0 in the denominator. And so that's why we could say for certain, both from the graph and from our derivative, that the derivative of f at 3 does not exist. So this is actually not a really good statement. Same thing up here is that I actually should be saying f prime of 3 does not exist. The derivative is defined here, and it is defined here. It's just not defined right there at 3. Okay. The reason why that's relevant, again, is those when the derivative is either 0 or it does not exist, those are potential candidates for maxes and mins. So it's just important for us to keep that in mind. We're going to talk more about that on the next video. See you guys then.